the S matrix, which includes all possible transitions from state I to state F, after sandwiching that matrix by the initial and final state, the answer is final state projection onto the wave function at time t in the interaction picture. And that was the transition amplitude, right? And this is very simple integral on time ordered exponential. An argument of that exponential is minus I over h bar integrated over time. That is the potential in the interaction picture. Actually, we have obtained this, but let us redo the calculation using interaction picture. Transition amplitude from initial to final state, neglecting order v squared or higher, is delta fi, and the first term minus I over h bar integral of minus infinity to infinity. And what I have to do is evaluate this interaction picture potential from the initial state to final state. Okay, do you remember that these I and F, those are the eigenstates of the unperturbed Hamiltonian, right? And they do not include the time evolution. They are constant. So they are evaluated just at t equals 0. Alright. Then this Hamiltonian reads the energy of the final state, and this Hamiltonian reads the energy of the initial state. And energy exponential is factored out here. I over h bar EF minus EIT. Okay. When this interaction is independent of time, then this part can be factored outside. And we usually define, you know that this time evolution factor for the unperturbed Hamiltonian has been already factored out, and we end up with the Schrödinger picture potential, right? This is Schrödinger picture potential. So I always have minus I over h bar to the potential in the expansion, right? The powers of minus I over h bar is the same as the powers of the V potential V. So as a convention, we just put this minus I, attach this minus I to the potential. And we just define this initial state to final state matrix element of the Schrödinger picture potential to be minus I MFI. So that means just MFI is I to F and Schrödinger picture potential. Alright. Then we remember that this is just a 2 pi delta function. So it's better to write it as a minus I MFI. So transition matrix element. Okay. So if we want to compute the transition rate, we have to compute the transition probability first. That is the square of this transition amplitude. Because our way of writing the transition amplitude is by making use of perturbation theory by order, it's good to express the powers in V. So this transition amplitude AFI is sum of AFI 0, that is a zeroth order in V, and first order in V, and second order in V, and higher order in V. Okay? So, if I want to compute the transition probability, I have to square the sum, right? So when I square it, the sum's order is a little bit complicated. At leading order, that is zeroth order in V, it is just AFI 0 squared. Because zeroth order contribution is this one only. If I want to compute the first order in V, then the only possible way of first order contribution is product of this guy and this. But this is complex number, so it is one guy is without star, the other guy is its own complex conjugate. So there are two terms, two crossing terms, so the result of order V contribution must be 2 times the real value of AFI zeroth order times AFI first order in complex conjugated form. What about the second order? If I want to find the second order, I have square of the first order. I have the square of the first order. However, I still have this another possibility that zeroth order multiplied by second order. So this part, 2 times the real part of zeroth order and complex conjugate of the second order. But we will find that the Fermi's golden rule considers only this part. And in order to be consistent in perturbation theory, in orders in V, then we have to compute these two. So this contribution was missing in the Fermi's golden rule. Okay? But for the time being, let us repeat the calculation that has been done already. The confirming the previous calculation is important because we have developed a different way of computing the transition amplitude. So we'd like to reproduce everything first, and then in the next class we'd like to compute this part. Okay, transition probability calculated up to this can be computed enough by using true terms, right? This guy multiplied to the zeroth component will be computed in the next class. Okay. So this is delta Fi, and this guy I have. Let us replace everything by transition matrix element. And this is transition matrix element M. Right? Okay. I think I don't have to explain in detail because we have done the same calculation already. This is zeroth order component and this is first order component. If I square it, I have delta Fi. It is either 0 or 1. Okay? If F equals I, then it is just 1. If F is not equal to I, then it's 0. And this was the case for Okay. I have 2 times real part. 2 times real part. Okay. If I put this guy in here, 2 times real part is like that. So, however, this guy is multiplied by delta Fi. That means F must be the same as I. So, but it is not summed over I. So diagonal component and its own complex conjugate, because potential is Hermitian. Its diagonal component is real. So that's the reason why we do not have this part. So order V contribution vanishes exactly if the potential is Hermitian. Second one, the square of the second one. So I have absolute value of the transition matrix element and over a factor 2 pi over h bar squared. And I have square delta function. And in the previous class we have explained it in detail, right? If I have a product of a square delta function, what I have to do is just to put the argument 0, but it is not really infinity, but it can be regularized by taking the finite time, and after taking the ratio we can again take the limit as t goes to infinity. Then we will find that the transition probability changes as time goes on. It is linearly divergent. So if I take the ratio, transition probability is increasing as time goes on. So I take the ratio to the time, interaction time, then this is the rate of transition rate from I to F state. And the value was like that. As I already told you, however, we have omitted the order V square contribution at the amplitude level. And that contribution in the interference term between 0th order, 2nd order may contribute. I'm not sure. Interference term between 1st order and 0th order vanishes if the potential was Hermitian. But I'm not sure. Before we compute explicitly, I don't know whether this guy survives or not. So we will compute that part, that is this, in the next class. Thank you.